This is the second piece of Graph Theory Basics. We will continue to learn the terminologies and jargons of graph theory, which will be used throughout the course. In the previous lecture, we learned about the degree centrality as a measure of how important or influential a vertex is. But there are many others. Closeness of a node measures how centrally located a node is. It gives us a sense of whether a node is like Daejeon Station or like Ulsan Station on the national railroad network. Ulsan is well connected to other cities, but its location is, comparatively speaking, at the periphery rather than near the center of Korean railroad network. If we measure the distances from node I to all the other nodes and compute the average, it's sort of farness. So by inverting this quantity, we define closeness. In case a graph has disconnected components, and thus some distances diverges to infinity, this alternative measure of harmonic centrality may be more meaningful. Now let's think about all the shortest paths that connect a pair of nodes U and V. There may be more than one shortest paths. Then an informative quantity is how many of these shortest paths is actually passing through the node I, right? By summing all these fractions for every possible pair of nodes existing in a graph, we can define the betweenness centrality. Maybe I have to mention that BC, betweenness centrality, can be equally defined for edges. Vector centrality is based on the adjacency matrix we learned in the previous class. Its defining equation is given like this. An intuitive interpretation of eigenvector centrality is that as a node is connected to another central node with high centrality, it is likely the same sort. And they will be determined in a self-consistent manner by this eigenvalue equation. Note that the centrality index xi is also on the right-hand side. So xi is actually determined by the neighboring nodes j. Right? So this is an eigenvalue equation. In principle, there are as many eigenvalues and eigenvectors as the total number of nodes, but we choose the dominant eigenvector, which is associated with the largest absolute value of eigenvalue of the adjacency matrix. Right. The cut centrality is a generalization of degree. While degree counts the number of immediate neighbors, cut centrality counts all the nodes that can be connected, that can be reached through a path, with the contributions from distant nodes being penalized according to this power law, lambda to the power of n. The PageRank centrality is behind the huge success of Google search engine. It has been the winning feature of the search engine Google and represented a revolution in the way we access information on the web. It is named after the term web page and co-founder's name, Larry Page. PageRank works by counting the number and the quality of links to a page to determine a rough estimate of how important the website is. The underlying assumption is that more important websites are likely to receive more links from other websites. Except for this lambda factor, lambda 1 minus lambda as a prefactor, It resembles eigenvector centrality. The only modification compared to eigenvector centrality here is the denominator kj, which is out degree of the neighboring nodes. Okay, so we will come back to this technical point sometime later when we will study the diffusion phenomena on networks. So for this toy model called Krachart kite, looks like a kite, right? The most central node varies depending on which centrality measure we use. So if you are concerned about the degree centrality, the black dot is definitely the most central node. If you are talking about betweenness, the green node is definitely the most influential, most central node, right? And likewise, we can find the most central node in terms of closeness, and so on. Here we see the distribution of various centralities over the same sample network. Okay. Closeness and harmonic centrality looks pretty similar. And degree and eigenvector centrality show a certain level of correlations. But different centralities have different rationale. They may be based on the flow or transfer across network or on the structural cohesiveness. So an appropriate centrality for one problem is not necessarily the right choice when applied to a different problem. Right. Another important metric for a node is the local clustering coefficient, Ci, here. It captures the probability that my friend's friend is also my friend, which is called transitivity in the context of social network analysis. C sub I is defined as the number of triangles that include node I as one of the three vertices, divided by the total number of potential triangles that can be formed by node I and its neighbors. So the values are bounded between 0 and 1. Then what about the clustering coefficient of nodes with degree 1? It's a matter of taste, but used to define it as 0. So if you look at this sample network, this red node with degree 4, its clustering coefficient in the first graph is 6 out of 6. So every possible triangle is already realized here. Right? The second one here has 1, 2, 3 triangles out of 6. So one half of clustering coefficient, Ci. And the last one, since we have no triangle at all, so the clustering coefficient is 0. In addition to the clustering coefficient of each vertex node, we can also think of their representative value, which is the algebraic mean of the local clustering coefficient over the whole vertices. This is a handy single number that characterizes the transitivity of a given network. But there is a criticism that this kind of average over an average is often not very informative. If you're interested, you can go look up Google with the keyword Bolobash paper, 2003 paper. An alternative way of characterizing the transitivity of a network by a single number is the global clustering coefficient, which is based on triplets of nodes. A triplet is 3 nodes that are connected by either 2 or 3 undirected edges. The former, the 3 nodes connected by 2 edges, is called an open triplet, and the latter is called a closed triplet. Interestingly, these 2 clustering coefficients, global and average clustering coefficient, can be often quite different. Right? Then which should we use? It depends. It depends on the context of your research problem. All right, so far we have discussed the characteristics of a graph based on individual vertex or an edge. We also defined the distance metric on a network and introduced the breadth-first algorithm. Now, before we will survey the real-world networks and explore their characteristics, I'm going to tell you about another characteristic of a graph itself. Bipartite is a graph where nodes are divided into 2 independent or mutually exclusive sets, and the edges connect only the pairs of nodes belonging to the 2 different sets. As you see in this sample graph, a bipartite is composed of 2 disjoint sets of nodes, yellow circles and green, olive green squares. And there's no edge between the same kind of nodes, right? There are no nodes between yellow circles or green squares. Actually, bipartite is quite common. If you remember the movie star network, it is a graph composed of the movie nodes and actor nodes. Scientific collaboration network also has 2 different components. One is the author, scientist, and the other is the paper node. Right? And metabolic network, the chemical reaction network occurring inside a cell, is also made out of reaction or enzyme nodes and chemicals or metabolites. And as we shortly see, the disease-gene association gives another good example of bipartite graph. An interesting property of bipartite is that if you think of a 2-step connection starting from a yellow circle here, you can come up with this subgraph composed only of the yellow circle nodes. Likewise, if you start from a green square and find the next nearest neighbors, you can obtain a subnetwork that is composed of only the green square nodes. This has some implications on the form of the adjacency matrix, and that's exactly one of the homework problems. Right. The disease-gene association is a key problem in biomedicine. It's critical in aspects of prevention, diagnosis, and treatment of diseases. Although gene-disease relationships have been investigated extensively, the majority of the mechanisms underlying these associations are yet to be elucidated. So despite this incompleteness of our knowledge, we can construct a disease-gene bipartite graph based on what scientists have so far established. Once this bipartite has been set up, we can project this bipartite into either disease space or gene space. So we see the association between the diseases that share the aberration of the same gene or mutation of the same gene, or between the genes responsible for the same diseases. This provides a new insight in a larger scale. As we see in the left panel here, spinal muscular atrophy is somehow related to various cancers, breast cancers, prostate cancers, and so on. On the other hand, here on the right panel, the oncogene KRAS is strongly related to the celebrated tumor suppressor gene, p53. This kind of bird's eye view provides a novel opportunity for drug discovery. For example, we may come up with a totally different use of an established anti-cancer drug for another purpose, which is the business in the so-called the drug repositioning research. Here is another creative graph reconstruction of a real-world phenomenon. This is about a food ingredient flavor component network. It's also bipartite. Or you can construct it as a tripartite, which is slightly out of the scope of this lecture. So, various regional cuisines and the culinary practices is reflected on the cultural diversity. But how can network science provide any meaningful answers to a question of whether there are any general patterns that determine the ingredient combinations in food, or any principles that transcend individual tastes and recipes? Along this line, a paper published in 2011 gives us a novel insight into the difficult task of identifying and gathering food that satisfies nutritional needs while avoiding foodborne illnesses. This process has contributed to the current diet of humans, which is influenced by factors ranging from evolved preference for sugar or fat to palatability, nutritional value, culture, ease of production, and climate. So again, as we saw in the previous slide, this ingredient compound bipartite can be reduced into a flavor network, from which you can draw some meaningful conclusions. Right, to conclude the lecture on graph theory basics, let me briefly mention Metcalfe's law, which was frequently quoted during the internet boom at the turn of millennium. When it comes to the value created by a network, the value of a broadcast network with centralized station and the passive viewers or listeners is proportional to the number of viewers and listeners. That makes sense if you think of TV commercials, right? On the other hand, in a decentralized network where the viewers or listeners are not a passive viewer anymore, but they start to communicate each other, the value of the network is proportional to the square of the number of its node, which are the communication devices in the original context. So the idea behind the Metcalfe's law is that the more individuals use a network, the more valuable it becomes. Indeed, if you remember the pager or beeper, beepy in Korean, it would be useless if there is no one to send a message to. The more your acquaintances or your friends have a beeper, the more valuable it is to you as well. The non-trivial part is actually the n-square dependence, which encodes that if a network has 10 members, there are 10, 9 divided by 2 equal 45 different possible connections. that these members can make to each other. If the network doubles in size to become 20, the number of connections doesn't merely double, but roughly quadruple to 190. This is an effect often called the network effect or network externality in economics. This is possible because while the cost of network-based service increases linearly with the number of nodes, the benefit is driven by the number of links, which increases as n squared. So there could be a threshold network size at which the benefit cost crossover takes place here. And the innovative technology eventually becomes commercially feasible or profitable. To further the discussion along this direction, Harvard Business Review published an article in 2001 where the value of a network can increase even faster according to exponential. The main claim involves an argument of the group-forming networks that allow for formation of clusters scale values even faster.